Hi, I'm just going to explain the molarity questions from this week's lab. So this is starting on page 9 of the lab exercise. And I'll start by just defining molarity. Molarity is really a term we use to discuss the strength or concentration of a solute. So remember, in a solution, we have what's called the solute, and we have the solvent. The solvent is the liquid portion, and it's usually water. Okay, and the solute is what's dissolved in the water or what's mixed in the water. And the way we determine how strong or concentrated that solute is in that solution is a term called molarity. And molarity is represented by a capital M, and it means moles of that solute over liters of solution. A mole is a specific quantity of that solute. It's a certain number of molecules of that solute called Avogadro's number. And if you look on the lab exercise, you can see what that is. It's 6.02 times 10 to the 23rd particles or molecules of that substance. So to find out actually how much of that we would add to make a solution of that strength, you're going to use a specific calculation that we're going to be talking about in a minute. So really this lab is about understanding what molarity means. We're going to be using this term molarity when we talk about properties of water, and also when we talk about the cell. Because when we talk about water movement in and out of a cell and how solutes move in and out of a cell, the concentration of those solutes inside and outside the cell is going to be really important. And we're going to use molarity to express that concentration of the solute. So first you have some questions asking you to calculate the molecular weight and the mole weight of various solutes. And a molecule weighs the sum of its parts. So I'll use water as our example, even though that's not a solute. I'll use water first, and then I'll do something a little more complicated than water. Okay, so water is 2 hydrogens and an oxygen. So 1 molecule of water is going to weigh 2 times the weight of hydrogen and 1 times the weight of oxygen. So it's going to be 2 times 1, because hydrogen weighs 1. And it's going to be 1 times 16. So this is going to give us 18. Now the question becomes, what units do I use? And that depends on what I'm measuring. If I'm talking about molecular weight, which is the sum of the atomic weights, then my units are going to be atomic mass units. If we're talking about mole weight, we're going to express mole weight in grams. And that's basically telling us how much 1 mole of that solute weighs. So your first real question is, what is the molecular weight and the mole weight of glucose? C6H12O6. So it's going to be 6 times the weight of carbon plus 12 times the weight of hydrogen, 6 times the weight of oxygen. And I really encourage you to use the periodic table that I have posted on Canvas, because it rounds the molecular weights. I'm sorry, let me back up. It rounds the atomic weights. So for each of these atoms, it gives you a rounded atomic mass. So it tells you that carbon weighs 12 daltons, or 12 atomic mass units, hydrogen weighs 1, and oxygen weighs 16. So now we can say 6 times 12, okay, plus 12 times 1, plus 6 times 16 is going to give us the molecular weight of glucose. And again, if you're talking about the mole weight, you're going to express that in grams. And if you're talking about the molecular weight, you're going to express it in atomic mass units. But your calculation is going to be the same. Okay, next comes millimoles versus micromoles versus moles. And in this case, milli and micro mean exactly the same thing that they did in the metric conversion problems. So milli, whether we're talking about liters, grams, meters, or in this case, moles, milli means 1/1000th of whatever that is. Liters, grams, meters, sorry, I don't know why I made that a capital G, or in this case, moles. Okay, micro means 1/1,000,000. So 5 zeros and then the 1. So again, same pattern as here. The other way we can write this is it takes 1,000 of the millis to equal the whole. Okay, so that means 1,000 milliliters equals 1 liter. 1,000 millimoles equals 1 mole. For micro, it takes 1 million. So it's going to be 1 million microliters, which remember we abbreviated with that weird little mu symbol. 1 million microliters equals 1 liter. That one means 1 million micromoles equals 1 mole. You're going to be using that to make some conversions later. Okay, the next question on page 11, they really answered for you, but we'll be doing a couple of those as an example when we get to the actual problems. So now let's get to the problems that start on page 12 and continue on page 13 of the lab exercise. So question number 1 is asking you to calculate the molecular weight and the mole weight of those 3 different solutes. And again, you're just going to add together the atomic weights. Okay, so the first one is sodium chloride, and that one's already been done in an example. It's adding together the mass of sodium and the mass of chlorine. So you've already done that earlier in the lab. Calcium chloride, it's going to be the weight of calcium times 2 of the chlorine. So whatever the chlorine weighs, you're going to say 2 times the weight of chlorine. And you're going to add those all together. So that's how you'll do number 1. And I think most people should not have a problem with number 1. Number 2, what does 1 molar solution of calcium chloride mean? One molar calcium chloride. Okay, this means 1 mole of calcium chloride per 1 liter of solution is what that means. Okay, so in that case, you would choose D and you would write out the answer. Sorry about this terrible glare on the board. It's getting worse as the sun comes up more. Sorry about that. There's not much I can do about it. Okay, number 3, converting to millimoles. I'm just going to do one example. Okay, so 10 moles equals blank millimoles. Remember, there are 1,000 millimoles. I'm just going to abbreviate it. In 1 mole. So 10 moles times 1,000 millimoles in 1 mole. Moles cancel out. So basically, you're just going to multiply by 1,000. So that would be 10,000 millimoles. So for each one of those, you're just going to multiply it by 1,000 for number 3. For number 4, to determine which one would taste saltier, you convert everything to the same unit. You either need to convert everything to millimoles or you need to convert everything to moles. It's totally up to you how you do it. And then you'll determine which one is saltier. And you'll use the same formula for converting. But remember, if you're going to do the millimoles, now you're going the opposite way. So you can either do 10 moles and divide by 1,000, so 10,000 millimoles, and then you could compare it with the other 2, or you could convert everything to moles and compare. Number 5 is a little tricky. And for that, you have to remember again what molarity means. Okay, so molarity equals moles of solute over liters of solution. And so this is just a division problem. It's 0.32 moles of sodium chloride divided by 3.4 liters of solution. And that will give you your molarity. I'm writing it backwards because I didn't know if I could fit it over here. So you'll just do that division problem and that will give you your molarity for number 5. Okay, 6 and 7 are the same as the example that was given earlier. And I'm going to work one of those for you. And then 8 is going to be different than those. 8 is really important because we're going to use that in a future lab that we're going to be doing. Okay, I'll just do one of number 6 and 7 since they're really the same. And there's really one trick that's important to realize on these problems. Okay, so all of these follow the same pattern. So number 6 asks us, how would you prepare 400 milliliters of a 1.2 molar solution of sodium chloride? And these all follow the same general formula. Oops, I just realized you can't see that. There you go, sorry. Okay, so moles per liter times grams per mole times liters. And what that's going to give you is grams, because watch what happens. Moles cancel out, liters cancel out, and I'm left with grams. Grams of what? Grams of solute. What this calculation is telling you is how many grams of the solute, in this case, sodium chloride, that we're going to add to make that solution. But that's not the total answer because it's saying, how would you prepare this solution? Step 1 is you calculate how many grams of that solute you're going to add to get that strength of that solution. I'm sorry, to get that strength of that solute in the solution. And then part 2 is going to be now explaining how much water you would add to get that total volume. It's also important to note that it's asking you for liters. So if you're given a question with milliliters or microliters or any volume that's not liters, you have to convert it to liters to use this equation. Otherwise, you can't cancel out liters. Okay, so you have to convert it to liters first. So let's work this example. We're just going to plug in the numbers. Moles per liter, that's our molarity. So this is telling us we have 1.2 moles per liter of sodium chloride. So 1.2 moles per 1 liter. Okay, grams per mole, that's the mole weight of our solute. So whatever solute this is in the question, you're going to calculate the mole weight. And in this case, for 6 and 7, we've already calculated that earlier in number 1. So we know that 1 mole of sodium chloride weighs 58 grams. So we have 58 grams for 1 mole. And look, now moles cancel out. Okay, now all I need to do is calculate my liters. 400 milliliters, if we divide that by 1,000, it's going to be 0.4 liters. 0.4 liters. Now liters cancel out and I'm left with grams. Okay, so I'm going to do this calculation and that's going to tell me how many grams of sodium chloride that I'm going to add to make that solution. And I'm going to let you do that calculation. You're just going to say 1.2 times 58 times 0.4. I don't know why this is so fuzzy all of a sudden. It was really clear earlier and now I'm so sorry about that. Something's going on with my camera. It makes me look better, but it makes makes the board look a lot worse. Okay, but that's only part of the question. The question is, how do we make this solution? Okay, we want 400 milliliters of this solution. So whatever we calculate here for how much sodium chloride we're going to add, the way we would make that solution, here's our container. We're going to say we're going to add blank grams of sodium chloride. Okay, so whatever you calculate here, that's going to go there. Okay, and then we're going to add water to make 400 milliliters. I should write that here. Total solution. We don't know really how much water that's going to be because we don't know how much water that sodium chloride has absorbed from the atmosphere. Okay, but we know we want it to be at 400 milliliters. Why would we not add 400 milliliters of water total? Because we already have some salt that's taking up some volume. And if we add 400 mils of water, now we're going to have way more than 400 milliliters of solution. Okay, so you would add your salt first, and then you would add enough water to get you to the 400 milliliter mark. And then, of course, you would mix that solution. So that's how you would explain how to prepare that solution. The same thing goes for number 7. How would you prepare half a liter of 1 molar calcium chloride? So for that, obviously the molecular weight is going to be different because it's a different solute. So you would go back to number 1 and look at what your weight of calcium chloride was. And now they've already converted it to meters for you. So your setup's going to be similar, except that your molarity is 1 molar, your weight is different, and your volume is different. But you're going to set that up the same way for number 7. And then last but not least, number 8 is a ratio. And it's important to realize what it's telling you. It's telling you now we're dealing with a liquid solute, and we're going to be making a dilution. Now, when we do the acid-base buffers lab, you're going to be getting a little bottle of sodium hydroxide. Okay, so sodium hydroxide is a strong base. It has a very high pH, usually around 12 to 13. And you're going to be getting a bottle of it that's concentrated, and it's actually 1 molar sodium hydroxide. And they're going to be asking you to dilute it and make a specific volume of this dilution. And the equation that they use for that is they say the molarity initial times the volume initial equals the molarity final times the volume final. So it just becomes a ratio. I actually like thinking of it as molarity 1, volume 1 equals molarity 2, volume 2. And either way it works. I just don't like thinking what is my initial and what is my final. I just like comparing the two as a ratio. In this specific question, it's saying you want to take your 1 molar sodium hydroxide and you want to make 15 milliliters of 0.1 molar sodium hydroxide. So now all we have to do to find out how much sodium hydroxide we would add is we want to just compare these numbers, okay, in a ratio. So we're going to put 1 molar here times volume 1. That's what we're actually solving for. And this is going to be the volume of sodium hydroxide, not water. You'll see that in a minute. Okay, equals molarity 2. This is our molarity 2. Times volume 2, so 15 milliliters. Okay, in this case, if you're wanting your answer to be in milliliters, which we do because this is going to be a small volume, then you can keep milliliters here because these are just comparing. There's nothing really to cancel out as far as the volume goes. We're trying to calculate a volume. So this you can keep in milliliters. You don't need to convert it. So basically we would divide each side by 1 molar and that would cancel that out. Divide this by 1 molar, moles cancel out, and now we're in milliliters. So really, you don't need to divide by 1, so it's just going to be 15 times 0.1. So that tells us 1.5 milliliters of sodium hydroxide is how much we're going to add. Now we need to calculate how much water we add. Okay, so 0.1 times 15 give us 1.5 mils. That's our sodium hydroxide. It's telling us we want 15 milliliters of this though. So how would we prepare that? The way we're going to prepare that is, here's our container. We're going to add 1.5 milliliters of sodium hydroxide into our container. And this is our 1 molar sodium hydroxide. God, I'm so sorry. Let me try that again. God, someday I'm gonna have a camera that covers the whole whiteboard so I don't have to keep looking at that. Okay, here's our container. Sorry. 1.5 milliliters of sodium hydroxide is what we've calculated that we need to add. And remember, this is our 1 molar sodium hydroxide that we got in the lab kit. And we're going to dilute that to make 15 mils of a 0.1 molar. And the way we'll do that is we'll add this first, and then we'll add water to get us to 15 milliliters. How much water will we add? Now we're talking about a liquid solute, not a solid solute. So now it's just the difference between the two. Okay, so that means we're going to add 13.5 milliliters of water. Okay, so this is going to be our water, 13.5 milliliters. Okay, and this is our sodium hydroxide, 1.5 milliliters of sodium hydroxide. And those together add up to 15 mils. Okay, so again, the way we calculated how much of the sodium hydroxide we add is using this formula. And then the way we calculate how much water to add is it's the difference between the total volume we want and the amount of the solute we're adding. Okay, if you have questions about that, please let me know. And if you want me to check your labs before you formally submit them, let me know. Just email it to me. Okay, thanks. Bye.